Welcome back, welcome back, welcome back. I'm Lisa Blackburn. This is my YouTube channel for everything I want to talk about science and math. And today we are doing chemistry, percent composition, empirical formula, and equilibrium. So this is unit 7. And yesterday we got through percent composition. Any questions about percent composition before we go on? Did that make sense? It was just molar mass, like we did for stoichiometry, and then we added to it that you figure out what percent it is, and like a lot of percents, you divide the little number by the big number and multiply times 100. So now, here's our next kind of problem. Remember I told you that this test will probably be just another mostly math test. It'll have a little bit of, it might have a little bit of multiple choice, but I'm not sure. It might be all math like the last one, which a lot of y'all thrived with that. 30% A's, that's really good. All right, so here's an example for empirical formula. So let me explain to you what that is. Okay, so a lot of times in mining, they will discover an ore, and then they get a chemical from that, and they have their chemical, and they can figure out what percent the chemical is of each element. But then they need to get from that to a formula. And the formula they get is a reduced formula. So like if you had hydrogen peroxide, H2O2, those 2's are both divisible by 2, right? So you could have a reduced formula for hydrogen peroxide, and it is just HO. Now, is that the correct formula for hydrogen peroxide? No, but through this math you're going to learn you can get to the correct formula. This reduced formula is called empirical formula, and the real formula is the molecular formula. So we're going to learn how to do the math to get the empirical formula and then the molecular formula. Do you sort of got the vision now? Very exciting because it's math, and we love math, right? Because math is great. Okay, so let me get my notes, see where we are. We made it. We did all that. Oh, I rewrote it. That's why I'm like, why doesn't it have it written down? Okay, so here's our example problem. Nylon. Those are supposed to be little legs in your picture over there. They look like. Did any of y'all ever read the Dr. Seuss book about the green pants with nobody in them? It was a Dr. Seuss book, and it's like a spooky book, and it used to scare my little kids to death when they were little. They're green pants with no one in them. So anyway, these are the spooky pants. You can color them green if you want to. All right, here's our example. It's not really supposed to be green pants. It's supposed to be nylons like stockings, pantyhose. Nylon is 63.68% carbon, 12.38% nitrogen, 9.80% hydrogen, and 14.4% oxygen. So they know the percents this is, and they want to get the formula from it. And how you get the formula is you start by getting the reduced formula, which is called the empirical formula. So first of all, you think about it. You can have any size sample you want. Because no matter if you have 1 gram of water, 100 grams of water, or a whole ocean of water, it still has the formula H2O. Does that make sense to you? So we could have any sample size we want, and it would still have the right formula. So in doing this problem, we assume that we have a 100-gram sample because our percents are based on 100. If you add up all the percents, you would get 100 because a whole is 100%. Are y'all following along with these mathematical concepts? No hat. Thank you. Not you. You're so used to that being told to you. Okay, so we're going to assume we have a 100-gram samples, and then we're going to take these grams and turn them into moles. Now, so this is sort of like we're going to do just a little bit of train tracks. Now, how do we turn grams into moles? What do we use? What goes with graham crackers?
Molar mass.
Molar mass, right? So we look on the periodic table, and what is the molar mass of carbon? 12. Look how y'all are memorizing that. Y'all didn't even have to look. So what we do is we draw a little train track here, and we put grams of carbon in the denominator. And remember, I like to do that with the sound effect as you push it catty corner. And what number goes with the grams? It's 12. And what goes on the other side of this 12 grams? Moles, because it's grams per mole. So it's 1 mole of carbon. Does that make sense?
Please help.
We're going to convert these grams to moles is what we need to do. That's our job. And we're going to do it by doing just the very first part of a stoichiometry problem.
But if the 12 is the molar mass, why is it gram?
Because the molar mass is the number of grams per mole. It's what Avogadro figured out, that it's a nice measurable amount. 1 mole of carbon is about a handful of carbon. So if I had to go get a mole of carbon for a thing, it's a very easy measurable amount to use in lab. We don't use cups and teaspoons, we use moles, and how we know the moles is the molar mass on the periodic table in grams.
So 12 grams of carbon, 1 mole.
Yep. Good? Everybody understand his question and got it? All right, so let's do the next. So you try the next one by yourself. Try setting up the nitrogen by yourself. I'm going to change colors. It'll make it easier.
Can we just go and do all of it?
Yep. All right, keep going with the hydrogen and the oxygen. I'm making mine different colors so it's easy, because it's a little tight. But you have pencil, so it's not so hard to write with. All right. So for the nitrogen, it's 1 mole of nitrogen over 14 grams of nitrogen. For the hydrogen, it's 1 mole of hydrogen over 1 gram of hydrogen. And for the oxygen, it's 1 mole of oxygen over 16 grams of oxygen. Any questions about how I did that?
Nope.
Okay, so now get out your calculator and everybody do it on your calculator. I'll go back to the colors.
Oh, I already did on my calculator.
Okay, so our first one is, and I want this one to 2 or 3 decimal places. You'll get it wrong if you don't have enough decimal places. Look up here once you've done it and check your answer, see if you got it right.
He wants to round the last number of each.
Yeah, to like 3 or 4 decimal places. Keep decimal places on this one. We're gonna need it, or else you will get the wrong answer. I only did this one for 2. Maybe it's got some zeros there. Orange. All right, did you get it?
I had a different answer for nitrogen.
For nitrogen, so do 12.38 divided by 14.
0.8842.
0.8842. Do more than 14. Do the whole thing on the periodic table. Do 14.067. Do that one. Let's see if you get it. Yeah, hydrogen is 1. That should be a
But I
left
got
off.
0.8838, not 37.
Either way, it's pretty, that at least you got. So that's a good point. You're going to need to use all the, not round as much on the periodic table. You need to use more of this. What I used was 12, 14. I used for hydrogen, for this one, I used 1.008 for its mass. But with that one, I used 16.00. Yes, Miss Evelyn? Talk loud.
the weight in grams, so it's just right?
Yeah, I think you're asking. You just look on the periodic table, get the decimal number, and really I rounded them, but you should use all the decimal points on this one. This one is going to come down to little decimal points, can throw you off. So we need to keep our decimal points on this one.
So the 16 for often.
You could have used 15.999.
It's on the bottom, and then the 1.
Yes, because of the units. The units are going to cancel out. Grams in the numerator, grams in the denominator. Let your units be your guide. Yes? Of which one? For hydrogen? Use 1.008. Yeah, I only put 1 gram of hydrogen, but really you should use more. The mass is what goes on the bottom. Because we have grams in the numerator, we got to have grams in the denominator to cancel out. Are we good? We're dividing by the molar mass. Okay, so next part of this problem is we look at our answers and we say, which is the smallest answer? Which one's the smallest? The nitrogen. So we're going to put a little star by nitrogen because it's smallest. So the next thing you have to do is you identify the smallest. So look at your numbers, figure out which one is smallest. Any question? Okay, I'm going to see if I can scroll up. But if not, I have a plan this time.
What is it called? The empirical formula?
What we're making is called the empirical formula. It's a reduced formula. Okay, so now which is smallest? It was nitrogen. And we're going to divide each of our answers by that. So our first one was carbon was 5.302 divided by 0.8837. And what we're looking for here is either a whole number, we're going to round it this time to a whole number, or one that goes to a half or one that goes to a third. We're going to round it to a whole number, a half, or a third. Well, this one is a whole number, 6. So now we're going to do the next one. I don't remember what color nitrogen was. We'll make it orange. So this one is 0.8837 divided by 0.8837. And that's what? Anything divided by itself is 1. Okay, so now we're going to do H. Well, I'll change the colors, make it easier. We'll do H as green. Okay, it's 9.720 divided by 0.8837. And what's that one? Round it to a whole number. 11. And then we do oxygen. Oxygen can be red. Oh, it didn't turn red. Red. 0.8838 divided by 0.8837. Round it off, what is that? 1. So this tells us our subscripts. Okay, so our formula is C6 N1 H11 O. You don't usually write ones, but by tradition, carbons and hydrogens go together. So the way it's more usually seen, we'll make it green, is C6 H11 NO. And you put a box, and that's the answer to our problem.
Why is it like that?
Why is that? Because we are carbon-based life forms. We're made out of primarily carbon and hydrogen. So the organic molecules are CHNOPs: carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur. And the number one thing that makes us hydrocarbons is that we are carbon and hydrogen, and those go together in organic chemistry. It's partly because it's what we are.
So we get it wrong if it's the
No,
one above that?
no, that's fine. But this is just by etiquette. You put them together. Yes?
I was putting in the same numbers you were, and I got different numbers from like all of them.
Look under your calculator, look at mode, and make sure you're on degree and not radian.
It's on degree, not radian.
It's on degree, not radian.
You put in the whole periodic
Yeah,
table.
then you put in the
You
whole
get-
math. Yeah.
Are you getting close? Like, were you able to get these numbers at the end? Okay, then that's fine. That's fine. But it'll work because these are based on real chemicals. The math will work. Okay, now notice it says sometimes you have to multiply so there are no fractions. We'll do a worksheet to make this more clear. So sometimes when you divide these, one of these, instead of rounding to a whole number, will be a whole number plus a half. Then you go through and multiply them all by 2 to get rid of the half, because we can't have halves in our subscripts. Sometimes you do them all, and one of them will be a third. Instead of it being 6, it'll be 6.33333. Then you multiply them all by 3, and you get the right answer. We won't do ones harder than that. They'll either be whole numbers, have a half where you need to multiply by 2, or have a third where you have to multiply by 3. Does that make sense? Not too terrible, right? Y'all seem to be understanding this pretty good. All right, the next idea of things, and okay, and then let me go ahead and tell you this too. From this empirical formula, you can get the molecular formula. You can get the real formula. How you do it is they will give you more information where you can figure out what you need to multiply the empirical formula by to get the molecular formula. Like I told you that hydrogen peroxide's empirical formula is HO, but its real formula is H2O2. You multiply it by 2. If you're going from empirical to molecular, they'll give you more information so you can figure out what the multiplier is. And that'll make more sense when we do some more problems. Okay? All right. So there's another thing called hydrates. And normally we have done a lab at this point where you would have known about the hydrates. Let's see if I can roll it. Aha, it's working good today. Okay, so some compounds have water crystals built into them. So they've got their crystal lattice, and in the crystal lattice there's water in it, but you can dry that water out. And it's called a hydrate. An example is copper 2 sulfate has 5 water molecules in its crystal. So how you write this is like this. You write the formula for copper 2 sulfate. Now, how do I get the formula? Let's review that. What's the charge on copper in copper 2 sulfate? Y'all remember this? This was 2 tests ago. It's 2, right? So this is plus 2. What is the charge on, what is sulfate? It ends in 8. So is it one chemical or more than one? More than one. So where do we find what sulfate is and what its charge is? Your polyatomic ion worksheet. So look at it, if you got it, and see if you can find sulfate and tell me what its charge is and what it is. What is the formula for sulfate? SO what?
4.
SO4. And what's its charge?
-2.
-2. So what do I do to write the formula? It's CuSO4. I can just put them together because they're the same. They cancel out.
Wasn't that a question on the test we just took? Wasn't that the answer to the question on the test?
I think it might be copper sulfate. Wasn't that our limiting reactant one? All right, so it's copper sulfate plus it's got water. So how it's written is that you put a dot right there for times, and it's got 5 water, so you put 5 H2O. That tells me that this has got water in it. It's a hydrate. Now, sometimes I can buy this from the chemical supply store anhydrous. An means not. So that means they dried it out. But here in Georgia, you open it up, and is it going to rehydrate? Oh yeah, we're very moist here. We have high humidity. So things that are anhydrous very quickly become hydrates in Georgia. It'll pull the water out of the air and it'll get hydrated again. All right, so we talked about this a little bit in the last notes, but I didn't test you on it. Equilibrium. So the equilibrium is gonna be on this one. This thing right here, going back to the hydrate, in lab, we're gonna dry this out. We're gonna get this chemical and we're gonna dry it out, and you can see what the difference in the crystals are when they've got the water in them and when they don't. We're gonna do it with our evaporating dish, our clay are we gonna use our rings, our wire mesh, or our clay triangle? I think we're gonna use our wire mesh, ring stand, and Bunsen burner. That's how we're gonna fire it up, dry it out. All right, the equilibrium condition. So we already know some reactions are reversible. Like rechargeable batteries. You're familiar with this. The battery in your phone is a chemical. As the chemical reacts, it produces electricity. When your battery is dead, you run the electricity through it backwards, and it makes it go from products back to reactants again. You can get the chemicals you started with again. When they stop going back and forth, so if you have in a beaker a reaction that's reversible, and you pour the chemicals in and it starts reacting and it starts making products, but then it won't make any more products. It's still got reactants in the beaker, and it's at this place of homeostasis. There is equilibrium. There's as many chemicals getting together to make products as chemicals coming apart to make the reactants again. It's not really like everybody's settled. It's just that it's the same amount going back and forth. And this point is equilibrium. Equilibrium. So, chemical equilibrium, same word again.
Spell with an I.
Equilibrium, is a dynamic state, meaning it's going back and forth, where the concentrations of all the reactants and products remain constant. It's at its finishing point. There is a way, and so one of the things we want to know in chemistry is how far does the reaction go? Does it go very far to completion, or does it stay closely a lot of the same products? Well, there's a mathematical equation we write to tell us how far the reaction goes, and it's called the equilibrium expression. Expression is just fancy for math equation. It's a formula, a math equation, that based on the concentrations in the balanced chemical equation that shows how much a reaction goes to completion. And then from it, you get a number that tells how far it goes that's called the equilibrium constant. Now, what we are learning right now is all part of your differentiation as honors. Regular chem's not going to get to learn this year, so enjoy your hidden knowledge, your extra knowledge. Okay, but everybody will get it in college. Okay, so here you have, this is considered the reaction. It's little a, big A, plus little b, big B, and you need to make your arrow go both ways. My computer won't make arrows both ways on top of each other, so draw that in. Little c, little d, big D. The big A and big B are the reactants. The big C and the big D are the products. The little a, b, c, and d are the coefficients of the balanced chemical equation. Do we feel okay about that? This is just the standard way of writing this. And I showed it to you last time. Okay, let's scroll up. Y'all are doing great. Y'all are doing good learning math this early in the morning. Sometimes it's hard to wake up and learn math. Okay, so then this is your equilibrium equation. This KEQ is going to tell us how far the reaction goes, and how you get this number is that you will be given in the problem the concentration of the reactants in the products. And you put them in this equation. So the concentration of, and products go over reactants. Everybody notice that the products are in the denominator, the reactants in the numerator. You write the concentration in square brackets, and you take it to the exponent of the coefficient from the balanced chemical equation. Are y'all okay with that?
So the ones on the right side.
So let's look at this one. Here we have ammonia and hydrogen getting together to make ammonia. We need to make our arrow go both ways. It's balanced. So we're going to write the equilibrium expression. We put products in the numerator or denominator? Numerator. So it's going to be the concentration of ammonia raised to the power of the coefficient divided by the reactants. So it's going to be the concentration of nitrogen times the concentration of hydrogen taken to the third power. And that's the KEQ. That's not so hard. And then if you were doing the problem all the way out, in the problem they would give you the concentrations. But there's one little complication. Of course there's one little complication, right? So make sure you understand this before I tell you the next bit. Yes, sir? That one? 3. It comes from that 3 right there. See the coefficient of the hydrogen? That 3 goes right here. That 2 goes right there. This one has an understood 1, so you don't put anything. You put reactants in the denominator, products in the numerator. Okay, this is the last little confusing bit. If it is a pure solid or a pure liquid, not aqueous, but pure solid, pure liquid, involved in the chemical reaction, they are not included in the equilibrium expression. So if when you do your little reaction, if it's got a little S in parentheses, meaning it's a solid, you don't put it in the expression. Or a little L, meaning it's a liquid, you don't put it in the expression. You just leave it out.
Wait.
You know how we learned that there you could tell the state of matter in lowercase letters in parentheses after the reactant or product? Remember that test before last on reactions? If in little parentheses after the element it's got a lowercase s, that means it's a solid, and you just leave that one out. If it's got a little L, that means it's a pure liquid, you just leave that out. You don't put it in if it's got a little L or a little S in parentheses. So sometimes you might have just a numerator, or you might have just a denominator, and then what should you put in the numerator? What's always understood to be there if there's nothing? A 1. So if all of your products were pure solids or pure liquids, you would have just a denominator and you'd put a 1 in the numerator. It's kind of fun. You learn all that math and now you have a reason for it. Isn't it nice to have a reason for math? The reason why you do math is so you can do science. And the reason why you do science is so you can make things turn colors, catch on fire, or blow up. Because it's fun. All right, so here's our next idea. And I'm really sure I'm not saying this in perfect French. Le chateliers principle. And we've already said if you say it like the French people do, it almost sounds like a bad word in English. So we're just going to say it the Dallas, Georgia way. Le chateliers principle. That's very Dallas. Okay. When a change is imposed on a system at equilibrium, system is just fancy word for you got a chemical reaction going in a beaker. And you do something to change its conditions. Okay, you're going to do something to your reaction. It's at equilibrium, it's making products just as fast as it's making reactants, and we decide to do something to it. Okay, good with me so far? When a change is imposed on the system at equilibrium, the position of the equilibrium shifts in a direction that tends to, let's make sure we get all right to see how you use the same word, to reduce, I didn't know if I said reduce or lessen or what, to reduce the effect of the change. Now, the idea behind this is nature likes balance. Remember biology, homeostasis? Remember osmosis? Remember how the water can flow across the semi-permeable membrane with no little water pump? It'll just do it because nature likes balance, trying to even out the concentration of salinity on both sides of the membrane. Did you learn that in biology class? About how you learned osmosis, hypertonic, hypotonic. Remember that? There's no water pump. The water will move by itself just because nature likes balance. These reactions will do Le Chatelier's principle just because nature likes balance. So if you do something to one side of the reaction, the equilibrium position will change to reduce the effect of that change because nature likes balance. Got that? Okay. So for example, you add more chemical you got your beaker going, and you decide to add one of the chemicals in your products or reactants. You decide to pour some more in there. See what that does. Okay, let's add a little more, see what that does. So we have increased the concentration in the products. So what I added was products, not reactants. I added more products to it, okay? You get more reactants and the equilibrium will shift to the reactants. Think of it like a push. Okay, so let me sort of draw this a little bit. Yeah, I guess so. We'll do reactants, products. Okay, so if I'm adding more products into my beaker, then it wants it to, this is a door. Okay, and so I add more products, then it's all crowded on the product side, and it doesn't like it. Too many products. So it'd be like if you had two rooms. Say there's a party and everybody's in one room. And it's just awful. People are bumping into each other. You can't breathe as often. Awful. So some people will leave that overcrowded party room and go to the less crowded party room, right? Oh, it's cooler in there. You can get a breath. Nobody's running into you and spilling your drink, right? So this is the party. You add more products, then they're crowded. They don't like that. The equilibrium will shift and make more reactants. Does that make sense to you? That's what Le Chatelier figured out. That if I add more reactants, what am I going to get? More products. So I want more reactants, I add more products. I make it go a little bit further. Okay? So so imagine here you've got your reactants and products. But this time, in my products, it's making a gas. Okay, can you imagine that? The gas bubbles off. These are the people who leave the party. So this room is way crowded. But the second room is right by the door and people are leaving the party. So this room's too crowded. Where are people going to go? They're going to go to the other room, to the P room. Does that make sense to you? So if you have a gas bubbling off in the products, it makes a void. Nature fills a void. Have you ever heard that expression? Nature is going to fill the void, and the reaction will shift to the products. If the reaction is in a closed container, meaning the gas can't just bubble away, then things are different. And we're not going to learn that. But if you want to learn it, and I encourage you all to do this, come back for AP chemistry and you'll learn what happens if the equilibrium is in a closed container. Don't y'all want AP chemistry? Next year you go take honors physics, but then the next year come back to me and you can have AP chemistry. And you can take another science too, because y'all are sciencey and smart. You can take AP physics and AP chemistry. You can take anatomy. You have a lot of choices your senior year. All right, so let's scroll one more time. One more scroll. We're missing. That was it. I was like, where's the Egyptian? Why do we have the Egyptian on there? Ammonia. Remember Ammon-Ra and ammonia? That's why he was on there. Okay. Like, share, subscribe. Science is great.